This is video 11.8. We're going to be talking about solubility curves today. This is something that you absolutely will see at least one question like this on the Regents where they're going to give you this. Why, you say? Because you have a reference table that is specifically designed to show you this and have you guys look at it. And that's table G. So what I want you guys to do is get your reference tables out right now and flip to table G. You may want to jot some of these notes that I'm going to make right there on table G in your reference table so that you have them to kind of look at. Otherwise, definitely make sure you write them down on the page, which is page 14, where we're going to be. And then we'll kind of talk through them. We're going to do a bunch of practice problems together. So a little bit unorthodox type of notes, but I think just kind of jumping right in and kind of explaining things as we go is the best approach here excuse me, for these solubility curves. So this is a screenshot of the same table that you have in your reference packet on table G. But again, table G, you're going to have a little bit more space, so that's why I want you guys to actually write this on your reference tables. And then you have them to look at throughout the rest of the year, and then you can, as you're studying and preparing for that Regents, and you're trying to remember the things that you wrote down in your reference table, you can then jot these down as well. So solubility, by this point, you should know what that definition is. If you haven't done your terms, guys, I've reminded you and told you over and over, you've got to know them. There's a lot of terminology here. So solubility, again, is the ability to dissolve. And what we see here on this graph is that you have a bunch of curves, a bunch of lines, and those represent specific solutes, okay? Pieces, things that have been dissolved in water. Now you might ask, well, how much water are they being dissolved in? And it tells us here over on the y-axis. Okay, so what we're looking at is you have the solubility of all of these different solutes. Okay, these different salts, different substances. Okay, and then you see how many grams of each solute is soluble in 100 grams of water. Okay, so this looks more confusing, guys, than it actually is. All this is saying is that, hey, we've got a beaker that has 100 grams of water in it, which, is 100 milliliters, but we're doing mass-to-mass ratios here. So that's not changing. No matter what solute you look at on this curve, it's not going to change. You have 100 grams of your solvent, which is water, and then what this is showing is that at different temperatures, how many grams of the solute can actually dissolve, okay? Now, there's three types of solutions that we can actually make. And these are the terms that I would encourage you guys to jot down on your reference table. I'm going to write them down right here, and then I'm probably going to erase them just for the sake of space. So the first that we have is called a saturated solution. You guys, I know, have heard this term before, whether it's been in this class or other classes. The best example of something that's saturated is like when things flood, right? The ground gets saturated with water so that it's full. It's to capacity, so that's what saturated means. It's full to capacity. In terms of the, that's a terrible way to write capacity. Okay, in terms of what these curves show for saturated, it means that it's on the line, okay? So if you're looking at the curves and you're looking for a specific solute, wherever that line is, so for example, this is Ki, all along this line, wherever you are, that means you have a saturated solution, okay? Everything is dissolved, the solvent cannot hold any more water, so it's full, okay? So if I go, say, somewhere under the line, like if I made a dot right here, which is under the line for Ki, what type of solution do you think that's going to be in terms of saturation? Well, if it's under the line, it's going to be unsaturated. Okay, it's unsaturated. It's not full. Okay, it's not filled to capacity. So this would be under the line. See how writing this on your reference table is probably going to be better for you. You can jot it down again on your page of your notes. That's fine. These are just the few terms that we need to be aware of. Now, I could also, there's a third option, I could also go above the line. So if saturated is on the line, unsaturated is below the line, meaning there's room to go, you have extra space to fill. What do you think above the line means? That would be supersaturated, okay? Okay, so this is filled over capacity. I'm going to erase that just because I ran out of space. Filled over capacity. So it holds more than it normally could hold. Okay, so in terms of the lines, it's above the line. Now, I want to star supersaturated, guys, because if we're talking in true terms of what a supersaturated solution is that this solution has been heated up and then cooled back down to where now it can hold more. Because if we look at our graphs here, overall, most of the substances, as you heat them up, their solubility increases, right? They can hold more grams of solution, or excuse me, of solute in their solution as they get heated. So in order to make a true supersaturated solution, you've got to heat the solution up and then slowly cool it back down, and that's when it will hold more of it. The best example that I can think of and use for this, something you guys may not be as familiar with, but down south when I lived down there, this thing called sweet tea, which if you're familiar with it, great. I personally think it's disgusting, but I know that I've talked to people who used to make their own sweet tea, and they would put like a dump truck size full of sugar into a cup of this tea to make it super, super sweet. The only way that you can actually make it so sweet is by heating it up. So as you're going through that tea making process, you heat the liquid up and you add extra sugar in there so that when you cool it, it now has extra sugar that it could not hold before in it. That's what a true supersaturated solution is. So another example of a saturated solution that I use is going back to my classic chocolate milk. You make chocolate milk and it's super, super chocolatey. What do you have a lot of times at the bottom, right? You have extra syrup just laying there. That is not necessarily a supersaturated solution, okay? That could just be saturated to where it got full, and I'm just going to draw a picture. You do not need to draw this. Okay, there's my cup, okay, and I've got all these dots. Those represent my solutes floating around in there. Well, again, a saturated solution can only hold so much. Once it gets full to capacity, it's then just going to store up more stuff at the bottom, and it's just going to sit there. Just because you have something at the bottom doesn't make it supersaturated, okay? This would still be considered a saturated solution because it's full, and once something's full, the excess particles, guys, just kind of sit around, okay? Think about floodwaters, right? Once that ground is full, does the water just go away? Does it keep soaking? No. The water then starts to flood. It's on top of the ground, and the ground is full. Okay, so note that there is a difference. Big thing here, what you're going to be asked about, supersaturated in terms of these lines, it's above, unsaturated is below, and then saturated would be on the line. Okay. If you have other questions about what I was saying, ask me in person. We can kind of discuss it. I have other resources I can show you as well to kind of drive that home, the conceptual mindset of what's happening at the particle level. Let's jump into the type of problems, though, that you're most likely going to see on the Regents. So here we go. Which salt is least soluble in water at 20 degrees Celsius? Okay, so we're going to kind of take a look. Now, salt, guys, means something. This is a review from back when we did our naming unit, which was, I believe, if I remember correctly, Unit 6. Okay. Salt means a certain type of compound. And what type is that? It's an ionic compound, guys. Anytime you see the term salt, it means or refers to ionic bonding taking place, so it's a metal and a nonmetal. So be careful, because not all of these are ionic compounds in here. Notice how we've got, SO2. Oh, we've got NH3. Okay? Those are not ionic compounds. HCl, not an ionic compound. So keep that in mind as you go through and answering some of these questions. That's how they'll try to trip you up. So, which salt is least soluble? So basically, guys, go here, 20 degrees Celsius. What's the first one you see? The hardest part's going to be following the line. So I encourage you guys to draw and use your pencil and actually follow the lines. Don't just try to eyeball it. Your eyes will play tricks on you when you have all these grid lines and other lines on it. So when we find that out, that's this salt right here, KClO3. Now, I'll be honest. I gave you this in your packet. If this picture, guys, is a little small for you, go and use Table G. This is the same one on the Regents. They won't even necessarily say, oh, according to Table G. They might just say, what's the solubility of this at this temperature? You have to know that it's Table G, okay? You have to know to look to Table G. Number 2, how many grams of potassium chloride can be dissolved in 200 grams of water? Now, notice what they did here, okay? This 200 grams is going to be important for us. If you just go to 80 degrees really quickly and say, okay, how many grams of potassium chloride? Oh, notice how you have to go from a name to a formula. Remember, anytime you go from a name to a formula, guys, and they don't give you prefixes, it's crisscross method. So this is a +1, chloride's a -1. All right, therefore we get KCl. All right, that's this guy right here. So this is my line that I'm looking at right along here. So we're going to go to 80 degrees. Go up. Oh, look. That's right here. Now, there's an estimation piece that you've got to go in, so be as close to as possible. I would say this is about 52 grams. But is that the correct answer? If I write 52 down here, that is not the correct answer. Because, again, if you look over here, knowing the basics, this, guys, is 100 grams of water. What this curve shows is 100 grams of water. How much water did we have here? They said 200 grams of water. So what do you think we have to do to solve this problem? Since we doubled the amount of solvent we had, we have to double the amount of solute. So this is going to be about 104 grams. And again, there's some wiggle room there because you might have said, oh, it's 51. You might have said it's 53. If you said it's something like 55 or higher, that's definitely not going to fly. So be as accurate as possible. If you need a ruler or a separate sheet of paper, use it. Okay? So those are the types of things you've got to think about as you're going through this. I want you guys to pause the video and try number 3 on your own. All right, so, So, 40 degrees, potassium nitrate. I got to figure out what the formula is. KNO3 is my formula for potassium nitrate. So I'm going to go find that one first. Okay, oh, that's this big one right here. I'm going to draw my line or follow. Oops, that's bad. Follow it down here. Okay, 40 degrees. Go up, see where it's at. I'm going to put a dot there just to kind of help me. It's about 65 grams. If you had 65 grams, you are incorrect. Again, you've got to look at the problem. This says 300 grams of water. Okay, that means it's triple the amount of the solute that this curve shows. So you've got to take 65 or your number and multiply it by 3. So the correct answer should be somewhere around 195 grams. Remember, again, there's a little bit of wiggle room depending on how you you estimated the original number. Number 4, which salt shows the least change in solubility across this temperature change? So this should be pretty easy. Which one has the slowest curve or the lowest slope? NaCl. All right, number 5, another take of a different type style question. This is where it's dealing with unsaturated, saturated, and supersaturated. 30 degrees Celsius, 90 grams. Oops, there's the bell. That was really long. 30 degrees Celsius, 90 grams of sodium nitrate is dissolved. So again, find sodium nitrate. All right, sodium nitrate's this guy way up here. All right, we've got 30 degrees Celsius. So I'm going to find my line right there. Okay. So in 100 grams of water, okay, now, did I need to go up to the line? No. Okay, because how much did I have? I had 90 grams. So 90 is right here. To be saturated, it would need about 95. But we only have this value right here. So is it below the line, on the line, or above the line? It's below the line. It's going to be unsaturated. Okay, so these are the style questions you could have. The last type you could be asked is like question number 6. So it says a saturated solution of potassium chlorate. Okay, and then I'm going to look up chlorate, ClO3. Okay, is formed from 100 grams of water. Saturated solution is cooled from 80 to 50. Okay, so first off, let's find those 2 points. So KClO3, it's right there. That's about 42 grams. Now we're going to cool it to 50. That's about 21, 22 grams. Okay. So it's saying how many grams of precipitate. So guys, when you cool a solution down after you have already made it saturated, okay, once you cool it back down, what happens a lot of time is that solute is going to crash or fall back out of solution in terms of a solid. So it's going to become a solid again. So this is just asking, well, how much would fall out of solution, how much precipitate would form? So we would take 42, we would subtract out the 22 that it ended up at, and we would get about 20 grams would form. Okay, so these last 3 I want you guys to kind of go through on your own. Pause the video. Those should be a little bit more straightforward, and then I'll go through the answers here in just a second. All right, so what compound shows a decrease? There's actually a couple different ones. So the ones that you could have here are SO2, NH3, and HCl. They are all decreasing their curves as you look at them from 0 to 100. Which salt is most soluble at 10 degrees Celsius? Remember, guys, salt is the key word here. It's got to be an ionic compound. That would be potassium iodide. Which salt is least soluble at 50? And this is the one that maybe you got right, maybe you got wrong. A lot of people are just going to say SO2, but SO2 is not a salt. So you got to go up to the next line, which is going to be KClO3. That is the correct answer. And it would not surprise me if they ask you a question like this on the Regents to test to see, do you know what salt means? And then which is least soluble at 90? That is going to be, again, salt. So it's not SO2, it's not NH3 because those are not ionic compounds, NaCl. All right, so now go ahead and do practice 5 using your table G, and I'll see you guys next time.